This is part 2 of chapter 1 titled Vector Spaces and section 1.3, some more definitions. This is the theoretical part of linear algebra that we briefly review or touch. The idea is that the rest of the semester will be about the computational matrix topics of linear algebra. But those require some theory of vector spaces. So the definition of subspaces: a subspace M of a vector space V over scalar F is non-empty subset of V that is close to vector addition and close to scalar multiplication. So altogether we have three conditions, and that means that the second one is that if you have x and y vectors belonging to M, then the sum x plus y is also in M. And when you scalar multiply x with an alpha scalar for any scalar alpha, this alpha times x vector is also in M. A subspace of vector space is automatically a vector space on its own right, since all the other defining properties are inherited from the vector space V. In fact, many textbooks define the subspace as a vector space that is a subset of another vector space. And the thing is that this definition would require then all the 8 vector space properties, the defining properties hold for this subset M. And then what these books do is that they state as a theorem after this definition that's actually enough to have these 3 properties for a subspace. Also, let me mention that this non-empty subset part is a requirement, and it's very important, although many times it's obvious and it's neglected. And the reason why it's important, because if somehow we have an empty set M, then for empty sets every property is true. And this is because when you want to say that the set has some property, that usually includes a if an implication statement, if-then statement. And if you have an implication, P implies Q, where P is false, then the implication is true, because basically it's not false, no matter what the truth value of Q is. We looked at the truth table of implication, so this is very important there, that if P is false, then the implication is true no matter what Q is. And one way to understand this is that to look at this classical example that says if it is raining, then there are clouds in the sky. But then if you negate this and you say that if it is not raining, then what does it say? Well, about the sky, there could be clouds, or maybe there are no clouds. It doesn't matter. And then for this reason, when M is an empty set, the statement that if X is in M, then we have the statement P of X, which means usually a property involving X, then this implication is always true no matter what P of X is. Because X is in the empty set, since M is an empty set, this is always false. Because there is nothing in the empty set. And in fact, there are horror stories in academia about mathematicians or PhD students who waste years of researching some special, interesting but complicated set, and then at some point it turns out that this is just an empty set, and that's why in particular it has a lot of interesting properties, but actually this is completely useless because nobody cares about empty set properties. So let's see an example. Last time in example 9 in the previous module, we discussed C01, which is the vector space of continuous functions on the interval 0, 1. Now let's consider a modification of this. Let's denote this with C sub 0 of 0, 1. And this is the functions from C0, 1. That means the continuous function over the interval 0, 1, such that f of 0 equals f of 1 equals 0. And it's easy to see that this is a subset of the continuous functions. We restrict the continuous functions to the cases where the value at the two endpoints 0 and 1 of these functions is 0. It turns out that this subset is actually a subspace. This C0 is a subspace of C over the, for example, the real numbers. First of all, to see that C0 is not empty, we have to find just one entry there. And for example, the 0 function, the identically 0 function, it's continuous. And we also have that this is in C0 because, of course, the function is 0 at the endpoints also, since it's 0 everywhere. So this 0 function is actually the 0 vector in this vector space. And in fact, in general, the 0 vector should be there always in all subspaces. So if you are looking for an example for a vector from a space, vector space or subspace, then you can check that whether or not the 0 vector is there. It should be always there. Then the second property is supposed to be the closeness to addition, vector addition. So in this case, this is function addition. If f and g is in C0, 0, 1, then we have to show that f plus g is also in C0, 1. And we know that the sum of continuous functions is continuous from calculus 1 or from real analysis. And then all we have to check is the endpoints, the value of the endpoints. So f plus g, the sum function, is evaluated at 0 by plugging in 0 separately into f and g and adding those values together. Since both of these are 0, we get that this is 0. And similarly, the sum function at 1 is f of 1 plus g of 1, which is 0.0, and that equals to 0. That means we have that addition, it's close to addition, because the sum function is also in this C0 set. Then the closeness to scalar multiplication, if f is in the C0 set and alpha is, for example, a real number, then alpha times f function is also in this C0. And to show this, well, we know that, again, multiple of a continuous function, constant multiple, is continuous. And then if you want to evaluate this at 0, then the way we evaluate alpha times f at 0 is that we evaluate f at 0 and multiply with alpha. But f of 0 is 0, since f is supposed to be in C0. And when we multiply with 0, any number alpha, you get 0. Similarly, alpha times f at 1 is 0. So the three properties hold. That means C sub 0 is a subspace of all the continuous functions C. Instead of this C0, if you consider another subset, C1, where we consider continuous functions that have 0 value at 0, but at 1 the value is 1. So this is still a subset of the continuous functions, because we assume that all these functions are continuous. But it turns out that the C1 is not a subspace of all the continuous functions over 0, 1, over the real numbers. And any of the three properties actually could fail, but well, the first one doesn't fail because you can easily find a function which is in this subset. And then we could consider just the vector addition or the scalar multiplication to fail. Let's consider vector addition. If you consider two functions f, g from the C1 set, then when you add together f plus g and you evaluate this at 1, you get f of 1 plus g of 1, which is 1 plus 1 equals 2. That means that the sum function at 1 has value 2. That means this is not in this C1 set because the function value at 1 is supposed to be 1. So the sum is not in C1. That means this set C1 is not closed to vector addition. I mentioned that the zero vector should be in all of the subspaces and vector spaces. In fact, if we just consider the zero vector and a set with only the zero vector in it, then this is a subspace for the vector space, and this is called a trivial subspace. So if you check the three properties, it's not zero because it has the zero vector. Also addition, you only have the zero vector, and if you add the zero vector, you get the zero vector, which is in the set. And it's also close to scalar multiplication because if you multiply the zero vector with alpha, you get the zero vector. So that means the scalar multiple stays in the set U. Next, we consider linear combinations. The sum as I goes from 1 to k of alpha I vi, which means we add together alpha 1 v1 plus alpha 2 v2 and so on up to alpha k vk. So this is called the linear combination of the set of vectors v1 vk with coefficients alpha 1 alpha k from the scalar field. As an example, we could consider three vectors. There are two vectors, so 2, 3, 3 minus 5, minus 4, 0. And a linear combination of this set of vectors is, for example, when you consider 10, minus 3, and 5, and you multiply the first vector with 10, second vector with minus 3, third with 5, and you add them together. So we do this scalar multiplication entry by entry, get 20, then also the addition and subtraction entry by entry, so we get 20 minus 3 minus 20, which is minus 9. Minus 3 times 3 is minus 9. And for the second component, we have 30 plus 15, it's 45, plus 0, it's 45. So it's a linear combination. It's resulting in a new vector. Another linear combination of this set of vectors would be just choosing the different scalars. For example, 0, 0, 2, then multiplying these, you get 0 vector, and then from the last term, we get minus 8, 0. Then once we have the linear combinations of a set, we define the span of vectors. If v1, vk is a given set of vectors in a vector space V over a scalar field F, then the span is the set of all linear combinations of the indicated set of vectors. And the way we write this is that the span of v1, vk is the set of linear combinations, sum as I goes from 1 to k, alpha I vi, where we choose all the possible scalars for alpha 1, alpha k. And it's relatively easy to see that this span is actually a vector space. More precisely, it's a subspace of vector space V. So we can actually prove this. We can show that the three conditions of a set being a subspace hold. First of all, it's non-empty. It's easy to see that, for example, V1 can be written as a linear combination of V1, Vk if you choose 1 for the first scalar and 0 for the others. So then you're left with the 0 vectors there that don't change V1. And that means that V1 is in the span, and in fact all vectors V1, Vk are in the span. It's also close to addition to show that if you choose two vectors u and v from the span of V1, Vk, then by definition that means u can be written as a linear combination alpha I vi, and v can be also written as a linear combination. It's supposed to be probably different from u, so instead of alpha we have to use some other notation for the scalars. For example, V is the sum of bi vi as I goes from 1 to k. For some scalars alpha I bi as I goes from 1 to k. Then to check that it's close to addition, we have to check that the sum is also in the span. So u vector plus v vector, that's the one sum plus the other sum. Then if you write out all these sums, we can use the commutative property that the order of the summation doesn't matter. And then we can use the distributive property that if you add together alpha I vi and beta I vi, then actually vi can be factored out. So then we get the sum as I goes from 1 to k, alpha I plus bi times vi. And it's in the span because it has the form that a sum with some scalars multiplied by vi. And these scalars are alpha I plus bi as I goes from 1 to k. Then the third property is that it's close to scalar multiplication. For that, we choose an arbitrary u from the span. That means u can be written as the sum as I goes from 1 to k alpha I vi for some alpha I scalars. And then for any alpha scalar, we look at how alpha times u looks. That has the form alpha times the sum of alpha I vi. Then we can use the distributive property 8 from the definition, which means that we can multiply through with alpha term by term, and also the distributive property 6 that says that when you multiply alpha with alpha I vi, then you can just combine alpha with alpha I, and then we get that this sum equals to this sum alpha times alpha I vi, where I goes from 1 to k. And that means this is in the span because it's a linear combination with scalars alpha times alpha I as I goes from 1 to k. Next definition is linear independence. A set of vectors v1, vk in a vector space V over F is said to be linearly dependent over F. So this is linear dependence. If there exists a set of scalars alpha 1, alpha k in F, not all of which are 0, important, such that the linear combination alpha I vi, the sum of alpha I vi, equals to the 0 vector. If we have this, the set of linearly independent vectors, then, for example, if alpha 1 is not 0, but then you could choose any other such index where alpha is not 0, we assume that not all of which are 0, so we could have alpha 1 0, but then we would choose another index for which alpha is not 0. Let's assume for simplicity that alpha 1 is not 0. Then if you consider this as an equation, alpha 1 v1 plus and so on up to alpha k times vk, then we can solve this for v1. So you take all the vectors to the other side with negative sign, and then you divide with alpha 1 through. So you get that the v1 vector can be written as minus alpha 2 over alpha 1 v2 minus and so on up to alpha k over alpha 1 vk. And then from this, what it says is that v1 can be expressed as some kind of sum or basically a linear combination of the other vectors, v2 through vk. And because v1 can be expressed in terms of v2, vk, we can say that v1 depends on v2, vk. So this is where the definition linear dependence is coming from. It depends on the others because if somehow v2 changes, then v1 will change. So v1's value depends on the values of v2, vk. And then what we have is also that if you have any u vector in the span v1, vk, that means U can be written as a linear combination of these V's from I equals 1 to K. And if you write it out, that this is beta 1 times V1 plus beta 2 times V2 and so on plus beta K times Vk, then we can replace V1 with this expression. So we get B1 times this expression for V1 plus the other terms B2, V2 plus up to BK, Vk. And then what you see here is that V2 are repeated, so we can multiply through with B1, and then we can combine the V2 terms with the V2 term and the Vk term with the Vk term. So what we get is for the V2 we get 1 B2 and then minus B1 times alpha 2 over alpha 1 as a coefficient for V2. Then similarly for V3 and then for Vk we have the coefficient Bk minus beta 1 times alpha k over alpha 1. But then what you see here is that this is just a linear combination of V2, V3, Vk. That means this is actually in a span of V2, Vk. So this argument, starting with the arbitrary element U of the span of V1, Vk, and ending up saying that this is in V2, Vk span, what we get is that the span V1, Vk is actually a subset of the span of V2, Vk vectors. It is also simple to see that the smaller set of vectors span is also in the span of the larger vectors, because this one, if you just take the first coefficient 0, you get all the linear combinations of V2, Vk, but this also contains other linear combinations, so this is a larger set seemingly. But since we already shown that the span of V1, Vk is in the span of V2, Vk, and also the other containment or a subset, then what we get is that actually the two spans are the same. So what we proved now is that the set of linearly dependent vectors can be reduced so that the span of the reduced set is still the same as the span of the original set. Yeah, that's what we did. We started with a linearly dependent set, and then we reduced it by throwing away V1, or basically expressing V1 in terms of V2, Vk. And we got that the span is the same. Then we can continue this process, so the span will stay the same if this new set is still linearly dependent. Then the next definition is linear independence. A set of vectors V1, Vk in a vector space V over F is said to be linearly independent over F if it is not linearly dependent. So that means that we have to negate the statement of linear dependence to get linear independence. That means it's not true that there are scalars alpha 1, alpha k, not all zeros, such that the linear combination alpha I, Vi, as I goes from 1 to k is 0. Another way to write this part, that not all 0, you can write it as there is a j index such that alpha j is not 0, and that the linear combination is 0. Then we can follow this rule of negation of the existential statement. The negation turns it into universal statement that for all alpha k, alpha 1, alpha k scalar, then we have to negate this other statement, and then this is an and, so and turns into or, and we have to also negate the other part of or. That means we get the statement that for all scalars alpha 1, alpha k, for all j, alpha j is 0, or the linear combination is not 0. That means the only way to get the 0 as a linear combination of v's is if all the alphas are zeros. Because one of them has to be true for this to be true, for the OR statement to be true. When all the coefficients alpha 1, alpha k are 0, in fact, of course this is then 0 since alpha I times vi is 0, and then the sum of zeros is 0. But then this is called a trivial linear combination because trivially this linear combination is 0 when alphas are zeros. So the only way to get 0 from the linear combination if all the coefficients are zeros. And this is just another way of saying that we cannot express one of these vectors in terms of the others. Because if we had that, then that means we could have a non-trivial linear combination giving 0 vector. And then it also means that we cannot reuse the set while keeping the same span. Linear independence has some consequences. This is formulated in remark 14 that says that if v1, vk is a set of linearly independent vectors in the vector space V over scalar field F, and if U can be written as a linear combination of V's with alphas, and also as a linear combination of the V's with betas for some choice of constants alpha 1, alpha k, beta 1, beta k, then in fact alpha j must be equal to beta j for all j index from 1 to k, which basically means that's a unique representation. So the vectors written as linear combinations have a unique representation with unique coefficients alphas. This leads to the definition of a basis. A set of vectors v1, vk is said to form a basis for a vector space V over F if, condition 1, the span of v1, vk equals the whole space V, and the second, the vectors v1, vk are linearly independent, or more precisely, the set of vectors is linearly independent. And both of these conditions are essentials. The first guarantees that a given set of k vectors is big enough to express every single vector of V as a linear combination of v1, vk. And the second says that you cannot achieve this with less than k vectors, and also that it's a unique representation. A non-trivial vector space V can have many different bases. Just to mention that if you have v1, vk, a basis, then if you multiply a basis element, for example, the first one with c for any constant c which is not 0, then this will be also a basis. It's easy to see that, but so you basically have infinitely many different bases, since you can have infinitely many different scalars multiplying any of the vectors. However, the number of elements in each basis for V is exactly the same, and this is referred to as the dimension of V, and it will be denoted by dim V. So that's the number of basis elements in a vector space. For example, if you consider the vectors 1, 0 and 0, 1, this forms a basis in R2. So that means actually the R2 has dimension 2. And also it's easy to see that you cannot have less than 2 vectors to form a basis in R2. So if you choose, for example, a single vector, the span of that single vector is a straight line through the origin in the direction of that vector. To see that as an example, it's kind of easy to work in R2 because it's nice to draw pictures of it. For example, if you take the vector 3, 7 in R2 and take the span of this, that means linear combinations, but that just means scalar multiple because there is no other vector to add. It's only one vector, so this is alpha times 3, 7, where alpha goes through all the real numbers. So that means that this is the set of all xy vectors such that x is 3 alpha and y is 7 alpha. And alpha is some real number. If you write this out as an equation, x equals 3 alpha, y equals 7 alpha, then you can solve, for example, the first one with alpha. For alpha, you get alpha equals x over 3, and then plug this into the second to get that y equals to 7x over 3, which is the equation for a straight line through the origin. So returning back to R2 again, what we see is that the dimension of R2 is 2, and in general the dimension of fk is k for every positive integer k. Finally, since we're going to work with matrices usually in this class, let me mention that the set of p times q matrices with entries f is a vector space, and usually it's denoted by f superscript p times q. Here the addition, matrix addition, is entry by entry, and the scalar multiplication is also entry by entry. Then a basis of this vector space is denoted by E sub ij, as I goes from 1 to p and j goes from 1 to q, where all the entries of Eij is 0 except the ij entry is 1. And that means that the total number of basis vectors is p times q, so that means the dimension of this vector space is p times q.